Okay, so for our very last talk of the week, I'm very pleased to introduce Zhiwei Yun from MIT, who will tell us about theta correspondence and relative Langlands.
Thank you. It's been a very intense but wonderful week, both mathematically, physically, socially, everything. So I really liked it. So I propose we all thank the organizers for giving us the chance to get together. Okay, so the talk is mainly about theta correspondence over finite field. It's based on joint work in progress two groups of co-authors, Jiajun Ma, Congling, Jialiang, and another topic I may or may not have time to talk about is the theory of character sheaves in the context of theta correspondence, which is joined with the Shamgar Gurevich. So I guess it was maybe during the COVID I heard a talk by Yanis on the BZSV relative Langlands duality work. That was the first sort of general formalism on this topic. First talk I heard, and I was immediately when I saw the theta correspondence was put in duality with Gross-Prasad branching problem, I was in love with it, and that's probably as much as I want to say about relative Langlands in this talk. The rest of the talk I will concentrate on theta correspondence. All right, so we will look over finite field characteristic not true. And start with a symplectic vector space, finite dimensional symplectic vector space over FQ. We have G symplectic group. So here I'm just viewing it as a finite group. A few points of the symplectic group. This group has a remarkable representation. So this way representation is, in some sense, it's like the standard representation. If G was not SP but a general linear group, the counterpart would just be Jialiang FQ acting on functions on this standard representation. Here to the nth dimensional vector space, for example, with C over C, Jialiang just acts by permutation representation. And when this symplectic vector space has dimension 2n, this wave representation is called omega. It also has dimension q to the n. So it's in some sense half or square root size of dimension a number of points indeed. So that's how large it is. And now we'll consider a pair of commuting subgroups in G. So suppose we start with two vector spaces, and the first one is a symplectic vector space. Second one is a quadratic space. And we'll give rise to symplectic group, orthogonal group. And we take V to be the tensor product of the two vector spaces, now equipped with a tensor product of two forms, so this is still symplectic. G1 times G2 will act on each tensor factor, so that maps to the symplectic group of B. And in the theta correspondence business, we start with the Wei representation of SPV and pull back to the product group and try to understand how it decomposes. This Wei representation pull back to G1 times G2 decomposes. Okay, so in the ideal world, it would behave like a sure-while duality. It would set up, we would like to set up a bijection between certain representations, irreducible representations of G1 and certain irreducible representations of G2. Okay, and something like this is really true if you don't work over a finite field, it would work over a local field. So we have the fact that the representation category is not semi-simple is actually helping you to select a unique quotient instead of considering all subquotients. But the actual situation is far from being a bijection. So this is how it decomposes is complicated in the sense it's not in general not a bijection between subsets of irreducible representation G1 and irreducible representation. What is true, though, is the restriction has multiplicity 1 property. So each pair if I start with a pair of representations, one for G1, one for G2, but it's complex irreducible representations, and this tensor product appears at most once. In the Wei representation. But aside from that, the general structure of which pairs appear it does not follow an obvious pattern. So here's work by Robert, Michel, and Bouquier. It's a fundamental work in this direction towards determining how theta correspondence decomposes. So they give a conjecture, an explicit formula for which pairs of pi1, pi2 appear. It's formulated using Weil group representations. Specific conjecture on the decomposition. And they include the conjecture for a variant of the situation where instead of taking this dual pair, they consider unitary groups. Much more recently, there's been two papers that prove the actual conjecture for the symplectic and orthogonal dual pair. So the first is by Jialiang around 19, and another group gave a much simpler proof. It was one of the group of co-authors I mentioned in the beginning, Jiajun Ma, and Jialiang reproved it a few years later, it's a much shorter proof. It's like 20 pages.
And what happens for GLN and GLM if you have two GLNs?
Yeah, I mean that's a much easier case was treated by.
Not only unitary, but actually GLNs.
It's I mean in that case they just act on the tensor product standard representation. It's much easier. So what I'm going to talk about today is yet another proof of. It's not about the whole decomposition pattern, but only about a very, you would say, simplest kind of representations, but using a geometric approach, and the answer will also be formulated differently. Or maybe I should just say what the answer looks like. Okay, so let me set up what kind of representations I'm gonna talk about, and then I'll formulate the answer in terms of these works, and then I will formulate it differently, geometric terms. We restrict to principal series. In the uniform principal series, these are the simplest kind of representations induced from the trivial representation on the Borel. Okay. So in this context, what we should look at is take the wave representation and take the fixed vectors under B1 times B2.
Do you see when the groups are split?
Yes. We assume the group is split, yes. Split groups. And even dimension of B2 is even. So this orthogonal space has even dimension. Otherwise, there's no such invariance. And we have to work with a different. Anyway, we only consider the case dimension B2 is even. So look at invariance under Borel, two Borels. This now becomes a module for the Heck algebra, which GI is just functions on GI bi-invariant under Borel, and naturally it acts on Borel invariance. Okay, so it's a very concrete question. So we have a bi-module for Heck algebra. We have different Heck algebras. They each look like, so each is governed by a while loop, maybe. So this is a type B, or so type of BC while loop. Ni is the rank of GI, which is the dimension, so BI over 2. And while loop, this looks like Wn is just Jialiang 2 to the n semi-directness. Which while loop, you have this deformation that gives the Heck algebra. And the representation theory of this Heck algebra is the classification of the irreducible representations is the same as the classification of the while loop itself. It was generic. So the problem is really about write it in quotation marks. We now have two while loops. Transitioning between Heck algebra and while loop, they have the same representation theory. So we're trying to decompose this bi-module for two while loops. And so the answer, well, the answer given by these papers are not completely the same. I'm gonna just, but it's not hard to transition between them. So the answer is the following. As a representation of Wn1 times Wn2, this looks like your sum over number L induction. So that looks like W and 1 minus L times diagonal WL times 2 minus L of some one-dimensional character. Okay, so it's a summation over L that's not exceeding N1 and N2. And then you just take, so each Wn will have a subgroup that's WA times WB, A and B add up to N. But then you take the diagonal copy of their this common size L part. Okay, so it's hopefully it's clear how this group embeds into the bigger group. And there's a specific one-dimensional character on these groups that you induce from. So that's the shape of the answer. So our goal is to, give a, we have a different approach and the answer will look different.
So is this multiplicity one that you said was projected? Is it clear from this?
It probably requires some calculation in the products, but it's not clear from outside.
In a one-dimensional character, all characters or some
Specific one-dimensional, so something like
It only has only two, right?
order 2, yeah, but each of them has like four one-dimensional representation. So there's a specific one that is
It only has
it's not the sign representation, it's the one that's like 1 on short roots minus 1 on long roots. Okay, so now so our goal is to reprove this, reformulate, reprove it, and answer in terms of Springer correspondence. We're talking about wild group representations. It is natural to expect that the answer would be given by a natural parameterization of irreducible wild group modules following Springer. Okay, so let me just briefly recall Springer correspondence. Any connected reductive group G. So there's by injection, there's an injection from irreducible representations of the wild group into pairs O and rho, where O is a nilpotent orbit. And rho is an irreducible representation of A of O. So A of O is the pi 0 of the centralizer of an element in this orbit. So it's pick any element in the orbit, you get centralizer. In our situation, all these are classical groups. This will just be elementary 2 group, abelian 2 group, so D mod 2 to some power for classical groups. So it's injection. It's usually not a surjection, except in type A. So certain, every nilpotent orbit will definitely appear with trivial rho. This pair is in the image. But for other rows, sometimes it isn't in the image, sometimes it's not. So we want to we want to write down this decomposition pattern using nilpotent orbits rather than directly using while loop representations. So now to formulate that answer, we need to introduce orthosymplectic Shamgar variety. That appeared in the work of Jialiang.
But it was suggested to us by Gayoto.
Okay, right.
Actually, flight if needed.
Should still match. So this is a very kind of a natural variety that's attached to the situation. So we start with this B. Let me call it up. Yeah, this B is a tensor product. I can think of it as formed when we want to be. So this is just using the form of V1, I can identify with its dual. And as such, I can think of an element in V as a quiver going from, well, just a linear map. But I can complete it into a slightly more interesting quiver because I have self-duality on both nodes. So if I have a map, I also get its adjoint using the forms of both V1 and V2. Now it makes sense to say when an element in V is nilpotent. For the nilpotent, if this quiver is nilpotent, namely, you compose using these two arrows, you compose enough times, you should get 0. Or it's same as saying compose in one direction is 0. So this way we get a nilpotent cone. V still carries V1 times G to the action. And this actually, this action has finite remaining orbits. And we'll see more about how orbits are classified. Now, as in the case of usual Steinberg variety, we will add some structures to nilpotent elements, such as flags. So starting with the MB, we will consider triples A, F1, F2. So A is just the element, the nilpotent element in B. F1, F2 are full flags, full isotropic flags. V1 and V2. And the requirement is that you go back. So A star, this is a map, this is a self map from V2 to itself. This preserves F2, A star A, preserves F1. Okay. That's just a very natural thing to write down. Okay, so now let's say, so this is the orthosymplectic Steinberg variety. Now let's define relevant nilpotent orbits. In the So let me first say something about how to visualize a nilpotent orbit in B. I said that we should think of it as a quiver. And here's a Jordan block for the quiver. So this is just as usual Jordan blocks. It's just a sequence of dots, arrow going in one direction. When you have two vector spaces and the arrows going in between them, it's like a zigzag. So you start from this vector, jumps to this, etc., and ends here. So that's a Jordan block generalized to quiver representation with two nodes. And these are the building blocks for general nilpotent elements in this V. So each nilpotent element is a direct sum of such Jordan blocks. But because of the self-duality on V1 and the V2, certain Jordan blocks have to appear in pairs. So if you have a map going just in one direction, it doesn't go back, then you must have similar map going in the opposite direction to match it. Yes, and V1 and the V2, since V1 is a symplectic space, this nilpotent orbit, the Jordan types for a symplectic group, should have even multiplicity for each odd Jordan block. And there's similar requirements for orthogonal group. So this kind of Jordan block is allowed as long as it appears with even multiplicity. So this will appear. Even multiplicity. This comes in pairs. Okay, so this is supposed to be more general. So you have, let's say, k dots here, k plus 1 dots here. That's one type of Jordan block. You can have as many as those. There's no parity requirement. Now, if you have k here and k, so it's not the which one is larger. It's rather the parity of this. So if this is even, you can just have such a Jordan block by itself. If this is odd, then it has to start life in the orthogonal group. And no, sorry, it doesn't have to. So as long as this dot is odd, so the other side is even, such things should appear with even multiplicity. So some combinatorics, we try to classify nilpotent orbits. And which ones are relevant? So the relevant ones are those relevant if it contributes to the top dimension, if you take pre-image in this Steinberg loft. And so concretely, in terms of these Jordan blocks, there's only one extra requirement. That is, if you this kind of zigzag and this kind of zigzag, the same size, but size are switched. These two kinds of Jordan blocks don't simultaneously appear. That's the only extra requirement. So you can play with small examples.
Can you describe relevance using like stabilizing?
It doesn't have to do with stabilizer. It's really about dimension. But okay, maybe it helps if I reformulate the relevance condition in terms of nilpotent orbits in the Lie algebra, not in this V, but in G1 and the G2. So an nilpotent element viewed as a quiver gives rise to two nilpotent elements in each, one nilpotent element in each Lie algebra. Moment map for theta correspondence. So it lands in nilpotent column. G1 and G2. So A goes to two compositions. And from the zigzag picture, you can just read off the Jordan blocks of the composition, right? This picture just gives a Jordan block of size 4 in G1, and Jordan block of size 3 in G2. Now, fact. So if you start with the O1 here, start with two nilpotent orbits. Well, first of all, they may or may not come from something here. If they come from something here, that thing may not be unique. There may be more than one nilpotent orbit in V that projects to O1 and O2. But for relevant, so for each O1 and O2, so this is a pair of nilpotent orbits in the two algebras, there is at most one. At most one relevant nilpotent orbit mapping to them. In other words, this there's a bijection between relevant nilpotent orbits in V and certain pairs of nilpotent orbits. So certain pairs which are also correlevant, so relevant pairs. And let me just tell you which pairs are relevant from this point of view. So you have a nilpotent orbit in the symplectic Lie algebra. So you have you just remember the Jordan type. See, so 3 have to appear twice. So that's an example. And Jordan type of O1, the Jordan type of O2, that's again some partition of 2 and 2. 4 has to appear twice. So something. So that just give an example. So you write the size of the Jordan blocks in decreasing order, O1 and O2, and the relevance condition is just saying the corresponding pairs of numbers, the gap is never bigger than 1. That's the relevance condition. Okay, now I'm ready to formulate. So the last thing is when I have O1 and O2, each has a centralizer group in G1 and G2, and I take the connected component group. So these are some finite in 2 groups. And I can do the same similar thing in for nilpotent orbit in V. I take its stabilizer and just record its connected components. I get another group, and naturally it maps to both. And that piece will come in formulation. So this is theorem. That says if I look at this decomposition of just Borel variant part of the Wave representation as a module for the while loop, it is isomorphic to there are some of relevant nilpotent orbits. O inside this NB. So this O will give rise to a pair of nilpotent orbits in G1 and G2. And for each of them, I will choose a row. So remember, in the Springer correspondence, I need a datum of an irreducible representation of A01, A02. A01, irreducible representation A2, such that, so they have to be compatible in the sense that when I pull back both to AO, they agree. Okay, so I have this data, and then the result is just whatever Springer assigns to this pair, O1, row 1. So that's an irreducible representation of the first while group, similarly for the second. That's the statement. So it's
So row 1 and row 2 are arbitrary here.
arbitrary as long as they're compatible. Compatible means take both of them, pull back to the stabilizer,
Yeah.
or here, they're good. So this formula, so just explicitly tells you which two Weil group representations appear together in theta correspondence.
I have a very ignorant question. I just didn't look the number. So usually in Springer correspondence, this condition that representation appears in the cohomology of the Springer fiber. Is it
Yes. Sorry, I forgot that. Yeah, you're absolutely right. This should appear in Springer correspondence, of course. In both cases, yeah. And here we are working with the full orthogonal group. So yeah, both are. This is not the Weil group of type D, but again, type B, BC.
But there is no claim that if row 1 appears and you have this compatibility, then row 2 appears. This is not.
No, this cannot be true because one of the numbers can be 0, for example.
One of the
This
numbers.
is a special case of it.
There's no number here. It's just.
And 1 or N2 can be 0.
That's right. Well, I fixed the two groups, so those are determined.
Right, no, but Roman's question was whether it's true that if row 1 appears in Springer, of course, that row 2 appears there automatically. And I'm saying that cannot
That's
be
okay.
right.
Well, there's no relation of priority.
But in this sum, row 2 is not determined by row 1.
No, it's not.
And that's
Say
why
which ones?
that's why it's the relation between all the O1 which occurs, for instance. It's like
Relation between.
between all the orbit O1, for instance, which occur. That's why one is maximal in some sense.
Which O1 can show up?
Yeah, we saw that. Oh, same.
Yeah, I don't have a clean answer, but I think based on this principle,
Yeah.
one can probably say something.
Yeah, because there are some conjecture about.
Okay, maybe we can.
Maybe.
Maybe
Is there a way to describe this matching in terms of like a Springer sheaf on the nilpotent contour V?
yeah, exactly. So that's rather it's just in terms of irreducible components. Yeah, or you can formulate it using Springer sheaf, but in more elementary terms, it's just about studying top homology. Yeah, maybe proof idea. To mystify statement is to this as a Weil module is the same as top homology of those in symplectic Steinberg variety. And after you realize this, then there's usual techniques of relating this variety to the actual Springer resolution of G1 and the G2. So the rest is sort of familiar geometric representation theory. But where does this come from? So I need to review a little bit of how one works with wave representation. So the mysterious thing about wave representation is there's not a single realization of it that allows us to see all the symmetry. So we have to make a choice to construct it, starting with a Lagrangian subspace in your symplectic space. One can realize wave representation as functions on functions basically on half of this vector space. And this construction allows you to see the symmetries of symplectic group stabilizing this Lagrangian. But it's not clear how the whole symplectic group acts on it. Nevertheless, this is probably the best we can do in this situation. We need, if you want to see the whole symmetry of symplectic group, you have to change the choice of L. And the remarkable fact is that as you change L, these different function spaces are canonically identified. It's a scalar issue. Okay, so now let's work with a specific L. So in the situation V is a tensor product, V, let's say, is a form V1 to V2. We choose a Lagrangian from V1, and that gives a realization of the wave representation as functions and from L1 to V2. Half of this original space. Now, how about its Borel invariance? So that's also easy to write down. These are functions with first there's a support condition. Let's call this space blackboard L1. There's some kind of nilpotent cone inside L1. And then there's I'll explain what this means. Some support condition and some equivariance condition. So what is N and L1? And L1 is just maps from L1 to V2 such that, so V2 is an orthogonal space. L1 has no extra structure. Now you can just pull back the quadratic form to L1. And this must be 0. That's the condition. So in other words, the image of this linear map is isotropic. So that's the some kind of nilpotent cone in this realization. That doesn't carry symmetry of B1 and B2. What can act is, well, B2 still acts because B2 acts on V2. B1 bar is the quotient. So is how an element in B1 acts on L1. This is an insight. This is a Borel in L1. So B1 is fixed stabilizer of a full flag where the Lagrangian step is this L1. In particular, anything in B1 induces an action on L1, and that part is some usual upper triangular matrix on L1. So there's this realization. somehow what's missing here from B1 to B1 bar, the difference is the unipotent radical of zero parabolic. Equivariance under that translates to the support condition here. Okay, so now it's pretty clear how to geometrize this. So if we look at sheaves instead of functions, consider this category. And we would like to, at the categorified level, we would like to understand how this category, how Hecke category, B1 and B2 act on this category. This is a module for the Hecke category. Ultimately, we would like to understand the structure of this category as a Hecke bimodule, but we're still some distance from there. But at least numerically, one can attach a characteristic cycle to each sheaf here. And where does it land? It lands, so these characteristic cycle will of course land in a cotangent bundle. Now I just view this as part of L1. And I calculate conormal orbits inside this vector space. And that calculation gives exactly okay, maybe more invariantly, so this guy modulo G1. The orthosymplectic Steinberg variety, we're up to some symmetry here because this doesn't involve choice of rail, here it involves. But anyway, so it's pretty much like usual story, sheaves on G mod B mod B. You take a characteristic cycle, it will land in the Steinberg variety. Usual Steinberg variety. So, but in our situation, this kind of invariance is sufficient to answer numerical questions such as how well group acts on the Grothendieck group, this category. So that's how we made the connection with the MB tilde. And, okay, so that's the first.
So do you get, you have two answers now, and do you get some combinatorial identities when you actually write down what they mean?
Yeah, it's an interesting, I certainly don't know myself, my co-authors may know, but I'm not aware of a kind of clean answer. Interesting. Okay, so now I want to say a little bit about the analog of character sheaves. Okay, correspondence. First, some general remarks. So when we study this relative Langlands situation, we have some spherical G variety. And at the level of functions, we want to understand how G acts on functions on X. Now, if we have two such things, one meaningful question is to study intertwining operators. G-equivariant maps from one space to another space. And you can think of course, every such map is given by a kernel. So that's the same as studying functions, diagonal invariant functions on G at x1 times x2. So these are, I think of these as analogs of, well, if you geometrize this, they are sort of character sheaves in the relative setting. Now let's specialize to theta correspondence, which is not of this kind. Okay, that's what makes it interesting. It's not cotangent of some spherical variety. Nevertheless, when we kind of categorify self-intertwining operators. So that's the same question, except that the situation is not polarized. It's not cotangent. I mean, this is sort of course, closely related to how omega would decompose. But what we want to say something more concrete about intertwining operators on omega to itself. What allows us to write down, the goal is to write down nice formulas for intertwining operators as concrete functions. The functions where, so
is it obvious that this algebra is commutative? I mean, you said that it's multiplicity one, but
Yeah.
from the definition, is it obvious that it's commutative?
for this one, so this is how this kind of Gelfand trick is used
Yeah.
to prove it. So indeed, you prove multiplicity one by understanding this ring, by rewriting it a little bit. Okay, so if you look at all C-linear endomorphisms as a vector space, this has a nice model. This is just all functions on V. And this is a canonical model, not for omega itself, but for its double. For the omega itself, you have to make a choice to write a model. For endomorphism, you don't need to make a choice. And therefore, if you study intertwiners, you're just looking at functions on V that are invariant under G1 times G2. So for example, for each simple direct summand in the decomposition of omega to G1 times G2, you have a projector. And they should give rise to some function on V. That's invariant under G1 times G2. And the question is how do you describe this collection of functions? So this is going to Shamgar Gurevich. It's not, I can't formulate it as a theorem. It's a construction. Construction of a class of simple perverse sheaves. Inside sheaves G1 times G2 equivariant perverse sheaves on this V1 tensor V2 that categorifies projectors to irreducible summands. But interestingly, so just as in the case of the theory of Lustig, character sheaves don't directly give you irreducible characters, so they only give almost characters. Character sheaves give rise to almost characters, which differ from actual characters by a non-abelian Fourier transform. Well, in this case, it's all abelian. Here, similar things happen. These class of simple perverse sheaves, these sheaves give rise to elements, maybe I call almost projectors. They're not quite projectors to irreducible direct summands. We don't understand the transition matrix between almost projectors and actual projectors. Okay, so there's no content here. I'm just giving a name to the functions attached to those sheaves. But I think it's an interesting question, try to study their relation. So just to give an example of what these sheaves might look like, I'll end my talk after that. So suppose V1 is an arbitrary symplectic space. B2 has dimension 2. So we are talking about SP something times O2. Maybe SO. So I'll write down these things working with SO. Okay. But the most scientific way of doing it is to keep the whole O. Equivariant sheaves. For sheaves. Now on this tensor product of B is V1 tensor V2. V2 is two-dimensional, and it almost has a basis. It has a canonical decomposition into isotropic lines. Let's choose isotropic basis. So I can write this, using that basis, I can write tensor product just as a direct sum of V1 with itself. Of course, that's specific to the O2 situation. So here are there are 6 simple reverse sheaves. That's kind of analog character sheaves in the situation. So what they look like. So constant sheaves on 0 times V1. So under this decomposition, constant sheaf on V1 times 0. There's a map from V1 times V1 to A1 given by the symplectic pairing. So I'm just viewing it as an affine variety. It carries this quadratic function given by symplectic pairing. That's called, yeah, so this is a pullback Artin-Schreier, and it's already a dual. So I mean, in the background, you have to fix an additive character to start with. That's the data you need to construct a Weyl representation, and that shows up here. And then there are 2 more interesting sheaves as the intermediate extension of 2 intersection sheaf of 2 subvarieties in B1 times B1. So this B is just pairs of vectors that are parallel to each other. And this Q is just pairs of vectors that are orthogonal to each other. Okay, so pre-image of 0 under this map. These are both singular varieties, and I take the IC sheaves. Okay, so this is the complete list of the so-called character sheaves in the theta correspondence situation in this example. We would like to have some kind of classification of these sheaves, but we are not there yet. Thank you for your attention.
Questions? So you mentioned relative duality in the title, and so it's next to subconjecture. So, like your results, can they be translated to the dual side?
Yeah, that's a very very good question. So I should mention this.
Can you repeat the question?
Basically, Roman wanted me to say something about relative Langlands and what happens here. What are the implications on the other side of the duality? So there's this wonderful conjectures by Frankelberg, Ginsburg, and Krafft that says, well, so suppose we are in the polarized situations, we have really spherical varieties on both sides of the duality. Then there should be some quasi-duality at if you look at B equivariant sheaves on X on the one side, and maybe weakly B equivariant Yes. On the other side, so the predictions, there's an equivalence intercounting the Hecke actions. Roman, this was in the paper dedicated to your birthday. It looks like a birthday surprise.
So it's not an April Fool Day joke. Someone's birthday is an April Fool.
So, yeah, this is of course, we are very interested in checking this conjecture in the case of theta correspondence. And of course, for sub pair, we're not there. Again, some ideas, but it's not true. You can kind of pass to numerical level by going to the cotangents on those. So this ND, this ND tilde is basically the cotangent of the theta situation. And there you have some usual cotangents. Maybe the zero cotangent of the stack. And in this paper, they checked in many cases, I think, including this case, that both sides at least have equal number of irreducible components. But one really would like to say more, which is the Y group actions also match. So that would be a shadow of this categorical equivalence. So in the top homology here, top homology here, it should be there's isomorphism as Y group modules. Now, in the case of theta correspondence and Shamgar Prasad, both sides have been understood. So I mentioned this part, but this side was also there's work by Jiajun Ma, who determined similar question for the Prasad situation, and indeed, actually, I'm not 100% sure whether we know they match, but certainly in examples they match completely as Hecke algebra modules.
But somehow when you say in matches Hecke algebra modules, means they actually have to really construct this. I mean, just knowing the number of reducible components is far from enough, right?
No, you're not enough. They both
complicated. Right?
Yeah, they both just work with the representation theory and arrived at the same well, I'm just saying both sides, the Hecke module structures are completely determined.
Oh, so you can just
You can just check.
So, but not that you can construct nice.
No, this hasn't been.
Yeah. So can you discuss how this is related to Lie superalgebra OSP V1 plus V2?
Yeah, I mean, only in a very superficial way. I understand this is the odd part. V is the odd part of the superalgebra. Okay, probably one can do something, or maybe you have already done something in a more general case.
No, I see that these Lie superalgebras are important if you want to do some kind of quantum versions of these things, and I think that if you're only
Here
doing
is not
but the classical version, I think that's kind of covered by this relative. I mean, that's just a special case of this relative Langlands. So there's like cases relative Langlands coming from Lie superalgebras. They have additional feature. They means of additional possibility for an additional kind of quantum deformation in the sense of quantum geometric Langlands. But here, I don't think it plays a role here.
So in other words, you obtain not this Lie superalgebra, but it's associated graded where the odd part is commutative.
And I mean, you just need a group with an action on something, and that something is supposed to be spherical variety or hyperspherical variety.
So this is what I'm saying. So commutator of two odd elements is 0. So it's like it's a degenerate version of OSP.
Let's say about this.
Oh, okay.
But I should say that this fact that these varieties have the same number of reducible components, that actually is checked for all these superalgebras. In the situation coming from superalgebras, this is now checked. Not that it helps to construct any kind of isomorphism like this, but Just the numerical statement is there.
Further questions?